Hi folks, this is Matt Ingram continuing with replication 4B, the JPR piece from 2010 in R. I apologize just quickly, I had called this slide 4A, replication 4A when I first started, but it is indeed replication 4B. So we were pretty far along. We had already done figure 4, we'd also already generated our grid reference, and we had done the OLS analysis, also known as the global analysis, and we had executed uh, the first GWR model after optimizing our bandwidth. So now we want to do our post-modeling diagnostics and visualize the local coefficients in figures 5 through 8. So let's go back to R and see how to do that. So here we are in R, and we were what in the script is labeled as step 10, the post-GWR diagnostics. So we want to check for stationarity on the back end, compare the distribution, say, of the OLS estimates to the GWR estimates we just produced. The Monte Carlo randomization test that we did before the GWR model offers a very precise way of doing this, but you can also do this somewhat more informally by comparing the 66% confidence interval around the OLS mean, the average effect estimated by OLS, with the interquartile range of the GWR estimates, which essentially represent 50% of the values, sort of the core of the 50% of the estimates. So one way to do that is to generate a histogram of the coefficients. We could do that with base income, but since the theoretical emphasis is on the terrorism index, let's do that here. So we can do a histogram. Just to remind us here of the GWR results. So the GWR results are listed up here. What GWR also generates is a spatial data frame. That's this SDF. So you can call it by calling the object that you created with the GWR command. We called our object GWR1, our first model with GWR. And you can call the spatial data frame with this SDF function. You can also summarize the spatial data frame. So it's a data frame with columns with each of the variables that were produced by the GWR object. So we can call the estimate of the terrorism index, all of the local estimates, with SDF $T. If you wanted to see what that looked like just in the console, you could call GWR1 the spatial data frame, and T. This should give you a listing, the column of all of the local estimates for each of the 67 units. And there you have it. So in Unit 1, the model estimated that terrorism has it's negative across all of the units, but that terrorism has this effect on growth, whereas in Unit 67 it has this effect on growth. So these are localized estimates of the effect of terrorism on economic growth. So we can create a histogram of these. So here you see that there's several units where terrorism has a very large, the magnitude of the effect is larger than some of the few units where the magnitude the magnitude is smaller on this end. There are several units where the magnitude of the effect is closer to 0. The magnitude of the negative effect is stronger in a few units down here at the end, on the left end of the spectrum. We could plot a density function. We could create a density function out of the T, the estimates of T, and plot that. So let's do that with this block of code here. That's that density function. And then we could add a histogram onto it. So there's our histogram again. These are not frequencies, but they're densities, right? So we've got the histogram of the values behind here, and we've got this smooth density function. And we could add the OLS estimate to this, right? So these are our geographically weighted results. These are our local estimates. So what's the single estimate, right? The one estimate from the OLS analysis, that's this one here. We're calling the coefficient for t from the OLS results. So that's the blue line. So this is the single coefficient estimated by the OLS model, right? That stationary, even, uniform coefficient across all 67 units. The OLS model said that was around minus 0.006. So you see that here reflected with the blue line, with the distribution of the geographically weighted estimates in the background, right, or alongside it. We could shade in the region also just to visualize this difference between the OLS model and the GWR model more informally. So we want to create a minimum left-hand value and a maximum right-hand value for the shaded region, and we're going to mark those minimum and maximums at one standard error from the blue line, one standard error from the OLS estimate. Right, so one standard error to the left and one standard error to the right. That area between those 2 points would give us a 66% confidence interval. Right, so let's execute that. Control R. You see it execute successfully over here on the left in the console, and then let's add it to our plot. So this is our 66% confidence interval under the density function of our GWR estimates. Again, the blue line reflects the single OLS estimate for the effect of terrorism on economic growth. The gray area reflects the 66% confidence interval. That is, we are 66% confident that the OLS estimate lands somewhere in here. It's still different from 0. And in the background with the red line, you see the density function, the distribution of the GWR estimates. So let's add the interquartile range of the GWR estimates and see what they compare like. First, let's add the median from the GWR estimates. So that is this green line. So you see the green line now. This is the GWR median. And now let's shade in with this last set of code the 50% distribution around the median from the GWR estimates. And that is this light blue area that you see here. Why is this important, or what does this tell us? This tells us that 50%, the heart, or the 50% core of values estimated by GWR lie within the 66% confidence interval of the OLS estimate. In fact, if you look at the blue line, the interquartile range from the GWR estimates is pretty much centered on the OLS estimate. The intuition behind these kind of more informal assessments of stationarity or non-stationarity is that the GWR estimates do not seem to meaningfully depart from the OLS estimate. All else being equal, it looks like the OLS estimate is a pretty safe estimate of the effect of terrorism on economic growth across all units. Again, the Monte Carlo estimate that we did before doing the GWR model is a much more precise way of doing this. And it can tell us with great precision, right, whether the relationship varies across units or does not vary across units. This is a more informal way of doing the same kind of analysis of stationarity or non-stationarity. So at this point, both the Monte Carlo analysis and this more informal analysis are telling us that it looks like the effect of terrorism on economic growth is fairly stationary. Again, this undermines the motivation for the GWR analysis in this particular project. Let's go ahead and visualize the results. One last diagnostic, with regards to the GWR analysis. One of the criticisms of GWR is that it can force the local coefficients to be correlated with each other, sort of generating a lot of collinearity or multicollinearity on your model. So you want to do some correlations maybe, or plot some correlations, examine the correlations among the coefficients. One way to do that is to use this code right here, looking at this pairs command. And here you see all of our variables from the model. And you see that indeed there is quite a bit of correlation, these linear relationships between the intercept and base income, between base income and education, between terrorism and government expenditures, between education and coastal units. So if you read the piece by Wheeler and Teufelsdorf, this is one of the flags or one of the concerns that they raise, right? And one of the diagnostic tools that they suggest checking for this kind of correlation among the coefficients. You could also plot this or export this rather as an image or in another format if you wanted to do so, but we won't do that right now. One of the more striking ways to use geographically weighted regression is to then visualize the results. So you could look at the pattern of I have various plotting functions here to look at the patterns in the data. If you plot them all alongside each other, it might not be very informative. With the SP plot using the data frame, it'll reduce the data to points. But this is not very informative unless this kind of plot is not very informative unless all of your variables are on the same scale. We could plot some of these other variables. We could calculate the t-values by dividing the coefficients by the standard errors, and we could plot t-values to see whether those are tell us anything about variations in significance. For instance, I've already generated these t-values, so you could plot the estimate. You could plot the coefficient for terrorism, so it's darker on the right, stronger on the right, and weaker on the western side of the country. This is Turkey in the background. You could also plot the standard errors, and then you could plot the t-values. Right? And here, one thing that you might... What if something didn't happen here? Hang on just one second. So I had to go back and regenerate the t-value. So here you see the t-value for the terrorism variable. Just going to hit Control Run again, and then this is the plot. You see it executes now. So this is a map of the t-values for each of the provinces, and you see that the absolute value, none of these t-values get over the absolute value of or an absolute value of 1.96. So that's telling us that at least at the 95% level of confidence, of certainty, none of these coefficients are statistically significant. None of these coefficients for t are statistically significant. That raises another concern. We could plot these also as polygons, or rather than points. So we could create a decile break here with this command, create some grayscale colors, and then plot this as here are the coefficients, fairly uniform across all the units, and there's the t-values. These are all of the t-values. Excuse me, just one second. Sorry, I just regenerated this command here so that it reflects the t-values. Again, not entirely clear. Here we'd have to do some interpretation of the legend or the values, how they're ordered, go back to the data table. A more intuitive way of doing this is to generate a new set of variables with only the statistically significant values. So here I'm going to generate this new variable called base 95 for the base income, the effect of the base income, that first predictor. It's going to equal the local coefficient, but then I'm going to make it equal to 0 if the t-value the absolute value of the t-value is less than or equal to 1.96. So if it's non-significant, I'm going to make it equal to 0. Otherwise, it's equal to the local coefficient. Same thing with terrorism. If it's not significant, it's equal to 0. Otherwise, it's equal to the local coefficient. Same thing with education, government expenditures, and the coastal variable. I did the same thing just in case nothing is significant at the 95% level. I did the same thing at the 90% level, so now everything, I'm going down to 1.65 with the t-values, with the absolute value of the t-values. And now, to the shapefile, I've added all of these variables. So the shape file adds the variable base 95 from the spatial data frame of the GWR object, adds the variable t95 from the spatial data frame of the GWR object, and so on. Same thing with the results at a 90% confidence level. So we're going to define some breaks here and then plot all of these findings, all of these results, trying to approximate these maps in figures 5 through 8 that are reported by in the original paper. So figure 5 reports the local coefficient of initial per capita income in 1987. That's the variable called base. Figure 6 reports the local coefficients for terrorism. You can see that in the paper they're reporting just the local coefficients with no cutoffs for significance. So these are just the basic t's. This is the estimates of of base. This is the local estimates for t, and then figure 7 and 8 show the local estimate for e and g respectively. These are the final empirical results, so we just want to generate all of these. So here is the plot for, excuse me, what happened here? Let's generate this breaks. And hang on just 1 second. Okay, so I just fixed some things in the coding here. So this is our first plot. Oh, come on. Okay, here we are again. I've just cleaned up the code a little bit. So now some more informative plots would be these quantile maps with 6 categories here. So the first one for the base income in 1987 is this block code, or this block of code. And there is a map. So you see that the coefficient is always positive, and these are only the statistically significant coefficients at the 95% level. So across the board, these local coefficients for the base income in 1987 are statistically significant, and they range from relatively small in the western part of Turkey to stronger in the eastern part of Turkey. We could do the same thing for terrorism. Again, these are only the statistically significant coefficients. And there you have it. And what is pink? Pink is 0. 0 means non-significant, the way we've just coded them. So across the entire geography, across all 67 units, the GWR model estimates, at least with the bandwidth that we used, estimates that the local coefficient is not statistically significant in any one of the units. So we could do this also for education, government spending, coastal. For education, it looks like this. You see that 0 is black, so on the western half of the country, the effective education is not statistically significant. In the eastern half of the country, the effect ranges from, is always positive, 0.04 to 0.06, so as education increases, economic growth intuitively, or as is expected, increases as well. We could do this for all of the predictors. A more interesting thing to do might be to combine all of the predictors into a single map So we would do this by generating 5 different objects with the plots we've just created, right? And so we're just generating 5 new objects, and then we would print those objects. So let's generate those. We just executed successfully in the console, and then let's generate this combined figure. Here you see the base income in the top left, the local coefficients of terrorism in the top right, education in the middle left, government expenditures in the middle right. You see that government expenditures are also not statistically significant. None of the local coefficients are significant. And then the effect of the coastal identity is not statistically significant in the western part of the country, like education, but it is in the eastern part of the country, like education. So you could also export this. If you picked out the whole code block instead of just the middle print part, you could export it as a portable networks graphic file or some other format. And then if you needed to, you could reset your graph space. There's another option for doing this. Note that these positions are not correct in this code, but you could place your graphs in different positions if you wanted to. You could also generate all of these maps at the 60% confidence level. I was just curious about, excuse me, at the 90% confidence level, I was just curious about the terrorism map, what that looks like, since that's the main variable of theoretical interest. So what does that look like? And this is what it looks like. So again, 0 is this light yellow, so terrorism, even at the 90% level, is not statistically significant anywhere in the western half of the country, and it is statistically significant in the eastern part of the country, and becomes more so, the magnitude of the effect is stronger in the southeastern part of the country. This is the finding that comes closest to the findings reported by the authors. Keep in mind that this is at the 90% level. Right, so they find that terrorism has this negative impact on economic growth, primarily in the southeastern part of the country. This graph shows that, or this map shows that, but it's only at the 90% confidence level. So you could, there's some more plotting options here. You could skip these. Another way that you could plot this, an alternative, is to export all of these values that we've just created, these 95% level and 90% level values, to another shapefile. So you could, we've already added them to our shapefile. Now we could write out this shapefile. We've added them to our object SHP. We know the file path to our working directory. We're just going to call it merge4 and use this driver. So with this line of command, you could export a new shapefile with all of these variables in it. Shapefile is I've already exported it into my working directory. It's this merge4. And we could open it, for instance, in ArcGIS. So here I've just opened that shapefile in ArcGIS, and I've plotted this same plot that we just did in R of the local coefficients of T at the 90% level. I've just plotted it again in R, making the 0 values blank. This is a little bit more intuitive than making them yellow, and then making the other values sort of progressively darker blue. So there you have it. That's another way that you could visualize this. In ArcGIS, you could add a nice legend and some titles and export it in different formats. So that's the way that I would visualize geographically weighted regression results, is to map them out, estimate the differentiate between the significant ones and the non-significant ones, and then map those results conveying significance. Again, if we went back to the combination map where we printed everything out, this figure nicely conveys all of our aggregate results, and we could compare these figures as we've just generated them at the 95% level to figures 5, 6. Here is per capita income, terrorism. We could compare them to figures 5 through 8 in the original article. Note that the authors in the original article do not differentiate between the significant and the non-significant coefficients in figures 5 through 8, whereas we do in these figures here. All right, well that's it for GWR. Thank you very much.